When a button is pressed, button state changes. A transition of button state can be from low to high or high to low. We can program the microcontroller to take either active high input or active low input. In active low configuration, microcontroller pin is pulled to the supply voltage with the help of a pull-up resistor, and when the button is pressed, the pin gets pulled to ground. But in active high configuration, pull down resistor is used to pulling down the pin, and when a button is pressed, it pulls the pin to VCC. But in both configuration, the state is changing, only the logic is inverted. The active low configuration is widely used for its simplicity and effectiveness. Let's connect the button with the microcontroller and use it to control a LED. Just search for active button in Proteus and select it. I am connecting the button to PB1 and the LED is connected to PB0. Now create a new project in MPLABX IDE. Choose microchip embedded and standalone project. Then choose the microcontroller. I am using ATmega32 for this example. Finally select the compiler. XC8 compiler should be installed previously. Give your project a suitable name. And click Finish. Add a source file to the source folder. Make sure the selected extension is C. Let's see how to write the code. Firstly, include the headers for I/O definitions and for delay functions. Then define the macro for setting the clock frequency. I will set it to 1 MHz. Inside the main function, set the data direction registers of port B. Setting the data direction bits to 1 makes it output and vice versa. I am setting PB0 to 1 as I have connected the LED to it. The rest of the corresponding bits of port B will remain 0. Remember about the active low button configuration? Let's use internal pull-up by setting the PB1 to high state. When the button will be pressed, then it will change the state of the pin to 0. Inside the while loop, first we have to check what is the state of PB1. If the state is low, then turn on the LED, else turn off the LED. For checking the PB1 state, current state of pin B needs to be ANDed with required state. It will give 0 in case of state change. If there is no state change, then the result will be 1. As the button press checking condition is providing 0 when button is pressed, it needs to be inverted to satisfy the if condition. To turn on the LED, PB0 is set to 1 and also PB1 is set to 1 as pull up for the pin. Inside of else, PB0 pin is set to 0 means the LED will turn off, but PB1 will be high for pulling up the pin. Lastly, a delay of 20 ms will ensure the stability of the code.
Huh? Oh my god, bro. Oh, hell no, man. What the
Okay, I forgot to discuss about button bouncing problem. So let's see what is this problem and how to solve it. So buttons are nothing but two separated metal contacts. By pressing the button, we are forcing those contacts to touch. At that time, the contacts literally bounces. Usually switches take a few microseconds to a few milliseconds to completely close. To solve the issue, we will wait until the bounces are gone. By simply putting a delay inside the if condition will do the trick. That is how we can debounce a button. Here I am putting 2 millisecond delay. 2 milliseconds will be enough for this. Let's compile the code. Copy the hex file path and paste it inside the Proteus program file option of ATmega32. Start the simulation. And look, it's working as intended. With the button press, LED is turning on. When releasing the button, LED is turning off. Next video will be on interfacing 7-segment display with microcontroller. We will see what 7-segment display is, how they function, how to control them, and how is the programming looks like. So stay tuned and subscribe to Electronscape for more such videos.